All right, last lecture, we had seen that bipolar junction transistors can operate in 4 different modes. And the reason for this is that we have 2 voltages here, base emitter voltage and base collector voltage. And you can see that there are 4 possibilities. When base emitter voltage and base collector voltage both are positive, both the junctions are forward biased, the transistor is in saturation. So we've written here saturation, F and F means both junctions forward biased. And when base emitter junction is forward biased, collector base junction is reverse biased, negative here, then we call it as a forward active mode. Here, FR, reverse active is when base emitter junction is reverse biased, collector base junction is forward biased, so we have reverse active, and cutoff is when both junctions are reverse biased here. So far, when we looked at the transistor action, we were basically looking at a forward active mode, where base emitter junction was forward biased and collector base junction was reverse biased. So we were seeing how transistor operates in this particular mode. And so I was telling you in the last lecture that reverse active is similar, except that the roles of collector and emitter are interchanged. So both of these we understand. The cutoff is very simple to understand. Both junctions are reverse biased, very little current flows, and we say the transistor is in off state here. So the last one then is saturation. So let's look at this one in a little bit more detail. So the idea here is as follows. I've drawn a graph here of IC versus VCB, collector base voltage, and the base emitter voltage is constant. All right, which means that this junction that you see here is biased at a constant voltage, which means that so it's biased at a constant voltage, and this voltage here between collector and base is what we are varying. So when collector base voltage, note, when collector base voltage is positive, we are in forward active mode. When collector base voltage becomes negative here, so this base junction is reverse biased here throughout, because collector is positive with respect to the base here, PN junction here. So this is base collector junction is reverse biased, and base collector junction is forward biased here. And this is, as I said, is what we call as forward active, and this one is what we call as saturation. So what we note here, and we have seen that earlier, that collector current in forward active is almost independent of VCB here, collector base voltage. It doesn't matter whether you apply small or large to the first order approximation. It doesn't matter what VCB is. When you go and forward bias the base collector junction, which means you enter into saturation, collector current remains constant for a while, that you see here, and then begins to drop. And can become 0, can become even, if you push it further, will go into even negative value. Okay, so this is the behavior. So first we see that when you bias collector base junction in the forward bias, initially it remains constant, and the reason is that initially the collector base voltage is small. You know, if you know that if you have a PN junction and you apply 0.2 volt, and 0.2 volt, it means that it is forward bias in principle, but the voltage is not enough. You're not injecting enough carriers. So that's why there's not much effect on the characteristics. It's only when you make the base collector junction sufficiently forward bias, sufficiently may vary from transistor to transistor, it may be 0.5 volts or 0.4 volt, then you begin to see the effects here. You begin to see collector current dropping here. So this is what we would like to understand. Why does collector current drop in saturation region once I make the base collector junction sufficiently forward biased here? So that's what we would like to understand. So let's look at it. Let's go inside the device and look at it here. So this is a description of a bipolar transistor. As usual, our base emitter junction is forward biased. So electrons are being injected here and holes are being injected here. And I've shown that this is, by the way, the direction in which electrons flow. The electron current would be opposite. Okay, so I've shown here that the electron current, let's say, is 1 milliamperes, and the base current, the holes that you see here, is 0.01 milliamperes here, just for the sake of discussion here. And collector base junction is zero biased. Okay, is zero biased, and therefore when it is zero biased, the collector base junction by itself, there is no injection of carriers. All right, next what I'm going to do is make it positive. Same base emitter voltage here. But I've now made it, the collector, I've made it negative, which means I have forward biased the junction. Now, all of you know when you forward bias the junction, what happens is that junction now, look at the lower part here, that junction injects electrons. Forward biasing means electrons will be injected from N to P side. And forward biasing also means holes will be injected from P to N side. So in addition to these two components that were there due to forward bias of base emitter junction, you get these two additional components here. This one because of forward biasing of collector base junction here. And this one also, when you forward bias a PN junction, you get both electrons and holes flowing in the junction here. So these are the two components here. So now, if we take a simplistic attitude right now towards the operation, so this is 1 milliampere here. So assume that this is 1 milliampere here. And now you're injecting something from here. And now note the direction. The direction is opposite to this one. So what is it going to do is subtract from here. So if this is 1 milliampere, let's say you've applied a collector, you've forward biased the base collector junction, and this is say 0.1 milliampere. So the net electron current then becomes 0.9 milliamperes. And suppose that this whole current is also, let's say 0.1 milliampere here. What will this whole current do? It will also subtract from the net current, because note holes flowing in this direction denote current in this direction here, while electrons flowing in this direction denote opposite. So the holes will also subtract from it. So now you can see that as I make my collector base junction more and more forward biased, this component of current that you see here will increase. This will also increase. And what will happen to the net current flowing across the junction? It will decrease. All right. So that's the reason why you find that once you forward bias the collector base junction, the current actually reduces. The current in a collector current, it reduces. Okay. That's the reason here. The initial current is here. And then in addition to that, when you forward bias the junction, you get these additional currents here because of the forward biasing of the junction here. And they subtract from the original current, and the current drops. Now we can understand why the current was not changing here. The reason being was I had forward biased it, but the forward bias was not enough, and these components were very small. And therefore, they hardly make hardly make a dent to this particular current here. Once you make the forward bias sufficiently large, then those currents become increasingly large here, and they cause the collector current to drop. As you keep on increasing the forward bias, the collector current keeps on dropping. Eventually, you can imagine that what you could do is you could make these two components that you see here equal to 1 milliampere here, which means that the collector current is 0. And this is the situation here. Collector current becomes 0 here. And now if you want, you could even increase the forward bias even more, and you could make these currents stronger as compared to 1 milliamperes here, and the current would reverse. Okay, so this is the situation in saturation region here. Both the junctions are forward biased, currents are injected here, currents are injected here, and as a consequence, the collector current is small here. Okay, so now note the following here. It's the same picture. Note that what happens is, as I make my collector base voltage stronger and stronger, IC goes down, as I've said. IC is going down because these two currents are subtracting. IB is actually going up. Does everybody see? IB is going up. Why? Earlier, note that IB is the current that goes from the base terminal. And what was it equal to? It was supplying the holes here. Now you're forward biasing the junction here also. So you're supplying the holes to this side also. So IB is actually going up. So what happens is, as you drive the transistor more and more into saturation region, collector current that you see here goes down, IB goes up, and in effect, what happens is, IC by beta IB becomes less than 1. Note that in this region here, I've already said the collector current is equal to beta times IB. Beta times IB here. IC equal to beta times IB, that's the forward active mode. So as you go into this region here, if IC is going down, IB is going up, it means IC by beta IB is less than 1 here. So that's one of the characteristics of saturation region. How do you tell? Suppose I give you a transistor and I tell you collector current is so much, base current is so much. How do you tell whether it is in saturation or not? You check this condition. You check IC, you check IB, multiplied by beta. Beta for a transistor is fixed. So IC by beta IB, you check whether it's less than 1 or equal to 1. If it is equal to 1, you know that you are here. If it is less than 1, you know that you are somewhere here. Okay, you are in saturation region. That's the test for saturation region. This is a picture now. Remember, these two are slightly different pictures here. In this case, I'm showing IC versus VCB, and the current is falling. VBE is constant. In the second picture, which is more common, I'm showing IC versus VCE, and it's plotted for different values of IB. IB1, IB2, IB3, IB4. What we are maintaining constant is not base emitter voltage, but we are maintaining constant is the base current. Base current is constant here. And I've already explained that collector emitter voltage, you can write it as VCB plus VBE here. VCB can be written as minus VBC here. And therefore, base emitter junction is forward bias, so I can write it as VCE as 0.7 minus VBC. And this point then represents the place where is a boundary between the place where collector base junction is reverse biased here and collector base junction is forward biased here. So if you look at a plot IC versus VCE, roughly around 0.7 is the boundary line where to the left of it saturation begins and to the right of it the forward active begins here. But note, the effect of saturation is not felt until you make this voltage somewhere around close to about 0.2 or so. Okay, then only you begin to see the effects of saturation. So as you go to the left of it, what is happening is base collector junction is getting more and more forward biased. For example, if I go at 0.6 here, at 0.6, we know that the base collector voltage is 0.1. 0.1 is a very small voltage, and therefore the forward biasing of the base collector junction doesn't have any effect. The current remains constant. As you go to 0.5, the base collector voltage becomes 0.2. Now it's more forward biased. So eventually the base collector junction becomes sufficiently forward biased and the collector current begins to drop. Okay, begins to drop and then eventually goes to 0 here. All right. This point roughly is people usually take it as 0.2 or so. Okay. Again, note IC by beta IB is less than 1 in saturation region. If you have in this region, IC will be equal to beta times IB4. As you go in this region here, note collector current is decreasing, base current is constant. In this case, one is maintaining by applying a current source to the base. So the base current is being kept constant here, and collector current is increasingly dropping, and therefore IC by beta IB is less than 1. So this is where the effects of saturation are felt. In this region, if you go, IC is still equal to beta IB. Theoretically, the transistor is in saturation region, but the effects of saturation are not there. It's almost like forward active mode here. You can see the current is constant. The real effects of saturation are felt in this region here, where IC by beta IB becomes less than 1. Okay? So that's the place here. All right. So a very simple model of BJT in saturation mode is here. Let's see if it makes sense. So this is what we are saying is in saturation region, I can think of my bipolar transistor like this here. Between base and emitter, I have a diode, which is okay. Between base and emitter. And so base here, emitter here, and collector here. Between base and emitter, we put a diode, which is fine. Between collector and emitter, I've put a battery. Now, these models are an approximation, okay? I've put a battery here, and we call it VC sat. So what we are saying is, if you are in this region here, this falling region here, this region is pretty sharp, and we can approximate it by a straight line that you see here. And the straight line, this voltage is what we call as the saturation voltage here, VCE sat. Whatever is the collector emitter voltage in saturation region. So what we are doing is, we are approximating this, all these characteristics, this falling characteristics by a straight line. And when you do that, straight line on this means the voltage is constant. Straight line means collector emitter voltage is a constant, and that constant part is what we put here. So that's a very simple model for transistor in saturation region. This value, as I said, for our discussion, VC sat varies from transistor to transistor. We'll take it approximately 0.2. Okay, we'll take it as 0.2. And so note, this voltage is 0.2. IC will not be equal to beta IB in saturation region. So wherever you see a transistor in saturation, I could replace the transistor by this particular model here. Not only that, I can make a model even simpler. The diode I can approximate it by 0.7 volt. So 0.7 volt here. So I think that's what I'll do here. So that's even simpler here. So approximate the diode by 0.7, and this is 0.2, and that's the model of a transistor in saturation region. Between base and emitter, you have a diode. So you approximate it by 0.7 volt. Between collector and emitter, The voltage is approximately constant. You approximate it by VC sat equal to 0.2. All right. So if the transistor is in saturation region, substitute this particular model and work it out. And once you work it out, the circuit, you will get some IC and IB. So normally what you would do is you would assume, let's say, the transistor is in saturation region, apply this particular model, right? Apply this model, you will get some value of IB, you will get some value of IC. How do you test whether the transistor, your assumption was correct or not? You check this relationship. You check this relationship. If IC indeed turns out to be less than beta times IB, your assumption was correct. If IC turns out to be greater than or equal to beta times IB, it means your transistor is not in saturation region. It may be in forward active mode. Okay. All right. So that was a saturation region. So now we know that the transistor can operate in forward active, reverse active, saturation, different modes. So what these models are valid for saturation region. So what I'm going to very quickly develop for you a generalized transistor model, a model which is applicable in forward active, in reverse active, in saturation region, any of those modes here. Okay. Now to do that, let's start with the forward active mode first. In forward active mode, we have said the transistor between base and emitter is a diode. Collector, from collector to emitter, I can write it as beta times IB. And IC is related exponentially with base emitter voltage. IB is IC by beta. So we have seen this particular model. Sometimes what people do is they redraw this particular model as follows. See, if you note the first one model, I can call it as a common emitter model here. Emitter is the common terminal between the input side and the output side here. So emitter is a common terminal. In the next case, I can take the same model and just rearrange it and make the base as the common terminal here. So emitter is the input side here and collector is the output side here. Now if I do that, note that between base and emitter, the diode will be in this direction. So that's fine. Emitter current will come out of this, just as emitter current here comes out of the terminal here, emitter current will come out here. Between collector and base, I have added a current here called alpha times IB, alpha F times IB. Note that this was beta F times IB, and I've called it alpha F times IB here. Sorry, alpha F times IE. It should be IE here because this is a current control current source here, so I should write this as alpha F times IE here at this particular point. Okay. Now, how do I find alpha F? Well, we know that IC, we are talking about forward active mode, so we know IC is equal to beta F times IB. We also know emitter current is the sum of collector and base current. IE is IC plus IB, which is evident from this particular picture here. IB flows here, IC flows from here, the two currents combine together and they come out from IE here. So IE equal to IC plus IB. Now from these two equations, I can rearrange and I can get IC equal to alpha F times IE. And alpha F is equal to beta by 1 plus beta here. So I can rewrite IC as alpha F times IE here and I obtain another model here. This particular model, I would call it as a common base model here. I've made the base as the common terminal here. Emitter is the input side here. Collector is the output side here. All right. So we have two current gains if you would like. Beta F that you see here, I call it common emitter current gain here. Emitter is common and the gain between output and input IC by IB is beta. And why F? Because we are talking about forward active mode. Okay, so that's the common emitter current gain here. Alpha F, I can call it as a common base current gain here. If base is the common terminal here, input current is emitter, output current is collector, the ratio of the two is common base current gain here. So sometimes you see a model like this here, sometimes you see a model of this kind here. Both are equivalent. There's no difference between the two. It's just a rearranging of terminals and writing the current in terms of emitter current, here writing in terms of base current here. Okay. So let's take this particular model, this one that you see here, and this one now again, I'll just simply write it in this manner here. Let's see if that makes sense. Same model here. The diode is turned 90 degrees here. Base is brought here. And the current source, note, current source is going from collector to base. It is going to collector to base here, right? And so it's the same model, except that it's turned maybe 90 degrees. This one is turned 90 degrees. This one is turned also 90 degrees, and we have written it like this here. Okay. Some little bit of change here in terms of terminology. This current we have written as IF. IF is the current flowing through this particular diode here. When you forward bias a PN junction diode, you know that there's a current flows through that PN junction diode here. So that's the current here. Now, and this one, if this is the current here, if we call it IF, then this current source that you see here must be equal to alpha F times IF. Just as it was here, alpha F IC and alpha F IE. So same thing, it will become alpha F IF here. Okay. So we have written it in this particular form here. All right. So YF because we are calling it as the forward active mode. You know, I'm using this particular model and I'll use it to generalize it to a generalized transistor model. So that's why I've changed the terminologies a little bit here, calling it the forward current and this one here. So what this model is basically telling you is, if you forward bias the base emitter junction, there is a current which starts flowing in the base emitter junction, alpha F, but a part of that current, alpha F times IF, starts to flow in the collector base junction also. That base emitter current gets coupled into collector base junction here. That's the transistor action that I was talking about. A part of this current flows here as well. Okay, so that's the forward active mode. So forward active mode current is here. This is what one is talking about. There is, when you forward bias the base emitter junction, there is this green current IN and there is this IP here. A part of this current here flows across the collector base junction. Note that this current keeps on flowing in. And this is denoted in this model here. This IN plus IP is the IF here. And IN that you see here is this current here. Okay, so this current flowing across this junction here, a part of this current, the green one, gets coupled across the collector base junction. That's the normal transistor action here. All right, reverse active, same thing. In reverse active now, base collector junction is forward biased. So we have denoted a transistor, a diode like this here. There's a current IR. I'm calling it the reverse current here, IR. And this current, a part of this current flows here. Same, alpha R times IR. Note the terminologies. IR is the current flowing across the base collector diode. And a part of this current, alpha R times IR, flows across the emitter base junction. Same model. Same model, except that now it's in the reverse active mode here. So now you can imagine what will happen is, forward active mode, I have this model. Reverse active mode, I have this model. And if I combine them together, I get a model of this form. I get a model of the transistor, which is a generalized model of the transistor here. In the transistor, I have two diodes here. One diode here and one diode here. The current flowing through this diode is, I'm calling it IF. Whatever is the current flowing in this diode, a part of this current gets coupled into the collector base junction here. Alpha F times IF. The current flowing in the collector base is IR. Whatever is the current here, a part gets coupled here, alpha R times IR. So that's the I've not derived it rigorously. I've just shown you that in forward active mode, I have one model, reverse active mode, I have another model. If I combine them together, I'll get something of this kind. So that's a more generalized model of a transistor here. And this is what we call as the Eber-Small model of a bipolar junction transistor. And I've also shown you here another picture of two back-to-back diodes. And you can see here why, if you just take two diodes in the lab, take a diode here and a diode here, and you connect them in this manner here, this is not a transistor. Compare this with this one. The unique characteristics of a transistor is not that it has just two back-to-back diodes. That you can easily take two PN junction diodes and connect them back-to-back. What is unique about a transistor is that a current which flows through this PN junction, a part of this current gets coupled here. It flows across the base collector junction here. Whatever current flows in this junction here, a part of this current flows here. These terms are the really important terms here. Alpha F times IF and alpha R times IR. These are the terms that denote the transistor action. Otherwise, take any two diodes and you get this here. Now you can see here, if I take two external diodes, what will happen is I don't get any coupling. Whatever current that you do here, the current will simply come out of the base. I have a metal contact here, the current will simply come out here. The transistor is constructed in such a manner that the electron current which is injected here It doesn't come out from the base here. It continues all the way to the collector here. Its internal construction is such that the current goes all the way to the end region here. Okay. So transistor then is two diodes that you see here, back-to-back diodes. But in addition, two of these current control current sources here, alpha F times IF here, alpha R times IR here. Okay. So from this model, you can understand the operation of transistor in any of those modes here. Forward active, what would happen is in forward active, this junction is forward biased, this junction is reverse biased, IR will go to 0. Reverse bias means IR goes to 0 here, this term will go to 0 here, and you'll get this diode and this current source here. Reverse active, this current IR will be there, this junction is reverse bias, IF will go to 0 here, alpha F IF goes to 0 here, and you get a model for reverse active. Saturation, both of them are active. Both these currents are there, and one has to look at which current is larger or smaller to figure out how much is the collector current, base current, and emitter current here. Okay. So this is the picture that we have then. We have all these four modes of operation, and the transistor then can be modeled in this particular manner here. Okay. Now, having said that, all our discussion will basically revolve around a transistor in most of the time will be in forward active mode. Very seldom will we find that the transistor is in saturation region. This course is about analog circuits, and in this analog circuits we'll be discussing amplifiers only, and we'll see to make an amplifier you want to bias it in the forward active mode. Okay, so this is the most important mode for us. And if you're using a bipolar transistor for digital applications where transistor is used as a switch, now switch can be in off state, then the transistor is here, and the switch can be in conducting state. Conducting state could be forward active, could be saturation. Okay, so when you're making a digital circuit, for a digital circuit, cutoff is important, forward active is important, saturation is important. All three are important. If you're making a amplifier, the most important region is the forward active mode here. But forward active mode, but we have to make sure that when we are biasing the transistor, our transistor does not go into saturation region. If it goes into saturation region, transistor does not work like an amplifier. You don't get any voltage gain. Okay, so we would like to be in this particular region here. So that's the region which we will explore in a little bit more detail here. Okay, now so far what I have said is a model like this of a transistor in forward active mode. So I've come back to forward active mode, and we have said that my collector current that you see here is a function of base current only, and base current that you see here is a function of base emitter voltage here. What it is showing is that the collector current is independent of collector voltage here. Now that's an approximation. Actually what happens is, if I go and look at my collector current here, collector emitter voltage here, I find that my transistor characteristics has a certain slope, which means that as I change if emitter is common, ground, if I change my collector voltage here, the collector current is changing, but not changing by a lot, but it is changing. Collector current is changing here, and this is very important for amplifiers. Ideal amplifier, as I said, we would want this to be flat, totally flat, but it is not. It is changing, and we have to understand why it is changing and what should we do here in order to modify this equation, in order to take that particular effect into account. So let's look at it in a little bit more detail here. So now what I've done is I've taken the same graph here and I've just plotted it on a different scale. And note that earlier the scale was from 0 to 10 volt, and now the scale is minus 60 to 20. So it's a very large scale. So the same graph is compressed here. Now on the same graph, now you can see the slope better. Okay, so slope is exaggerated here. Now what is interesting is I take along y-axis I have collector current, x-axis is collector emitter voltage here, and these are the graphs for different values of base current. Right? So now what is very interesting is if I take this particular graph here, this is for one particular value of base current, and I extrapolate it here. What would happen is it will extrapolate, eventually meet at some voltage here. If I take the second one and I extrapolate it here, it also meets at the same place here. If I take the third one, meets here. The fourth one meets here. They all meet at a particular point. And this point is what we call as a early voltage here. early voltage here. The voltage goes by the name of a person who first described this particular phenomena, James Early. And so the voltage, this particular voltage is named after him. And we call it the early voltage here, VA. Okay. Typically it's called VA. So now this is interesting. It says, this is active mode. It says that collector current in active mode is increasing with collector emitter voltage. It is changing with collector emitter voltage. How is it changing? It's changing linearly. It's changing linearly with voltage, and therefore I can write it in this manner. IC, so earlier we were writing IC was equal to beta times IB. Now what we are saying is, well, it does depend on VCE. And how does it depend on VCE? 1 plus VCE by VA. Because it's a straight line, you can see here, if I put VCE equal to minus VA, the current goes to 0. It extrapolates to 0 here. So that's a simple equation of a straight line. So all these curves that you see here, they all will extrapolate to VA here. So no matter what IB I take, the equation for my collector current then is IC is beta. Sometimes you will see I will write beta F denoting as forward active mode. Sometimes I'll omit. By default, unless we say something else, beta refers to forward active mode. Okay. Beta times IB, 1 plus VC by VA here. So that's the significance of my early voltage here. Okay, so the collector current is changing with voltage here. The change is small. A value of it may be, in this case, I'm showing a value equal to 50 volt here. So 50 volt here. So note that if IC is equal to beta times IB, early voltage is 50 volt here, and I apply 2 volt here. So if I apply 2 volt here, 2 by 50, so it's a small quantity. Okay, it's a small quantity. May not make, if you're doing a quick analysis, may not make too much difference to your collector current here, to the value. But we'll see at another place is very important. Okay. Now, why does this happen? Again, as I said, our interest is mostly in looking at the terminal characteristics, but very quickly, why does my collector current change with this voltage here? And this picture you can understand, this variation you can understand from here. So what happens is the following. If you look at now forward active mode, emitter base junction is forward biased, collector base junction is reverse biased. So I have this depletion region that you see here, shaded region here, depletion region here, and a depletion region here. Electrons are injected, they flow all the way till here. Holes are injected, they flow here. Okay. Now what happens is, as you increase the collector base junction, you are making the junction more reverse biased. As you make it more reverse biased, the depletion region increases here. The electric field increases and the depletion region becomes larger. You can see here. It would increase larger here also. So the boundary of depletion region that you see here, which was earlier here, now the boundary of depletion region comes over here. Because as you increase the voltage, the electric field increases, along with the electric field charge increases, along with charge then the depletion width increases. Okay, so this increases here. So depletion width increases, and as a consequence of what happens is the base width, the effective base width by the effective base width, which means that the region between the two depletion regions, that's the base width. Okay, the base width that you see here decreases. The base width decreases here because earlier the boundary was here and the boundary was here, and so the base width was larger. Now the base width is smaller. Now, how does it result in increase in current? Well, if you think about it, I've not said it explicitly here. If you think about this current here, you are injecting electrons, right? The electrons get injected and they come to the base. Now this region that you see here, the base is neutral. Why? Because the depletion region is here, depletion region is here, that's where the electric field is. Outside the depletion region, I have no charge, it's neutral. Now the question that you should ask yourself, this current that you see here, how does it flow? It's going from this end to this end, and how does it flow if there's no electric field? We said that there are two processes, drift and diffusion. So the current flows due to diffusion here. Now when you go into diffusion, what happens is, diffusion depends on the gradient. Diffusion current depends on the gradient here. And the gradient will depend on what the base width is. So as you increase the collector base voltage here, what you're doing is you're decreasing the base width and causing the current to increase. The electron current that you see here, it increases. Okay, so that's I can't go into the details. That's the subject of a different course, but that's in effect the reason why the collector current changes with collector base voltage here. Again, let me quickly tell: as you increase the collector base voltage, depletion width increases. As depletion width increases, the effective base width goes down. As effective base width goes down, the current is a diffusion current. As base width goes down, the current increases. Electron current increases. Hole current, as on the other hand, doesn't change much. Hole current is going on this side here. Okay, so hole current doesn't change much. The collector current is what is affected here. Okay, and so this is the phenomena that we call as early effect, and it comes about because of base width modulation. Okay, so now we have a better model. We said now, earlier we had IC equal to IS exponent VB by VT minus 1. Now we've added this particular term here. That collector current does depend on collector emitter voltage 1 plus VCE by VA here. Base current remains the same, and so we can write this as also as IC is equal to beta times IB 1 plus VCE by VA. So all of these, whether you write it in this form or you write it in this form, these are equivalent here. Okay, so the important point is now we know that collector current does depend on collector emitter voltage also, although the dependence is weak. It's a weak dependence here. Okay. Now I'm going to talk about some more effects in bipolar transistor. So we have seen early effect. Let's look at another effect here. This picture talks about variation of current gain with current. Now so far I've said I've been talking about beta, and I said beta of a transistor is given to you. Now when you go to a manufacturer, the manufacturer will not tell you one single value of beta. He will give you a graph like this here that you see here. Now, two things from this graph have to be noticed here. One is, and this is a schematic variation that I've simplified it and shown here. Beta is constant over a certain current range. When I say beta of a transistor is 100, over a certain current range, you will find beta is indeed 100. As you go to very high currents, beta will drop. As you go to very low currents also, beta will drop. Okay, so, for example, this is important because you may take your transistor and you may read that beta is supposed to be 100, make an amplifier, and you're driving too much current into your transistor. If you're driving too much current, you may exceed this particular threshold and your beta may actually be 10 or 20 or 30. It may be smaller. Similarly, you may be driving very low current into your transistor and your beta may be smaller. Okay, so to keep in mind, when we say beta is 100 or 200, it's over a certain current range here. Beyond that, it's going to fall. Higher currents and lower currents both. How is it going to fall? Well, you have to go and look at the manufacturer's data sheet to see how it is decreasing here. The other one is beta is temperature dependent, which you see from this graph here. This graph tells you at 125 degrees you have a certain beta, at 25 degrees you have a lower beta, and at minus 55 degrees, you have even lower beta here. So beta is going to be higher in summer and is going to be lower in winter. Beta of the same transistor here. So that's again something to keep in mind. Beta of a transistor is temperature dependent. It's a function of current here, higher and lower currents, and it's a function of temperature as well. Okay. These are important because when we design circuits, we want circuits to work in both summer as well as winter. Right? And you will see when we do amplifier, let's say the input resistance of an amplifier, of a bipolar transistor based amplifier, input resistance depends on beta. And therefore, if you are in summer, beta is higher, input resistance may be higher. Right? If you're in winter, input resistance is lower here. So you have to keep these things in mind when you're designing. If you're telling a customer that I guarantee an input resistance of 1K. Well, if he measures in summer, it's okay. If he measures in winter, if it's not 1K, he's going to complain. So you have to keep in mind how the beta is varying. And when you tell somebody that beta is going to be larger than 1K, then you have to make sure that at minus 55 degrees Celsius also is larger than 1K. Yeah. So when you make practical circuits, you have to take these things into account. Your circuits are supposed to work not just at room temperature, they're supposed to work at a range of temperature here. So you have to look at these variations into account here. Okay. I'm stating these things, although throughout the course, we'll take beta as 100 or 200, whatever, as a fixed value. But you should keep things at the back of your mind that beta does change. Okay. The other thing is we have said PN junction breaks down, and a bipolar transistor has PN junction also in it. So a bipolar transistor also breaks down. Now normally what would happen is my collector base junction is the one which is reverse biased, and therefore the collector base junction can break down, and therefore your transistor will not work properly, obviously. Now there are two ways in which breakdown voltages are specified. Again, if you read a data sheet of a transistor, one way is what people do is they keep the emitter open and they look at simply the breakdown of this particular junction. And we call this breakdown BVCBO. And you can see what it means is it's called BV refers to breakdown voltage, CB refers to collector base junction, and O refers to emitter is open. So what the manufacturer is saying, that he is quoting a value of breakdown voltage where he kept the emitter open and applied a sufficiently large voltage to cause a breakdown. And at what voltage does it break down? We call it as BVCBO. This is a common transistor, 2N222. Breakdown voltage is BVCBO is 75 volt. Another parameter that the manufacturer sometimes quotes is where the emitter is grounded and the base is open. Base is open, and obviously we call this breakdown BVCEO. So it's the breakdown voltage between collector and emitter, and the base is open. So that's another breakdown voltage that is quoted here. This breakdown voltage for the transistor is 40 volts here. Is usually lower as compared to this one. So two things it's emphasizing, it's telling you is that breakdown voltage does depend on how you operate the transistor. If your emitter is open, another emitter is open, you may get this breakdown voltage, 75. If your emitter is grounded, base is open, you may get 40 volt here. What it is telling you is breakdown voltage does depend on how you operate the transistor. Okay, so I just wanted to highlight that there are two different breakdown voltages here. Why this is lower is a little bit more involved. I'll not go into the details here. Another thing is, normally, as I said, base emitter junction you would forward bias. But by mistake, if you confuse between emitter junction and base emitter and collector, you may reverse bias the emitter base junction also, or in some circuit it may happen that base emitter junction gets reverse bias. You have to be aware that base emitter junction can also break down, and the point is to keep in mind the breakdown voltage of base emitter junction is much lower. For example, for this transistor is only 6 volt, and the reason is that the base emitter is heavily doped. When you make a junction heavily doped, its breakdown voltage comes down. So never take a base emitter junction and reverse bias it by 10 volt or 15 volts or whatever. You'll damage the transistor. Collector base junction can easily handle, as you just saw, 40 volts, 50 volts and all that. But base emitter junction cannot handle that. Okay, and I made a general statement earlier that bipolar transistor is not symmetrical. Emitter doping is much higher as compared to collector doping here, and that's why what happens is when you operate in forward active mode, you may get a current gain of 100. When you operate it in reverse active mode, you'll get a current gain of 1 or 2. It's highly asymmetrical. When you use collector base junction, you may get a breakdown voltage of 50. When you use emitter base junction, you get a breakdown voltage of 5. Okay, so these things you should be aware of, that you cannot simply interchange emitter and collector junctions here. All right. So far we've talked about NPN. PNP is similar. We have PNP, and the distinctions to keep in mind is the directions of the diodes reverse here. And now, so we have the same picture, except that note the difference here. Emitter base junction is forward biased when you make VEB positive. VEB, when you make emitter more positive compared to base, then you're forward biasing the base emitter junction, which means that VEB has to be positive. Similarly, collector base junction is forward biased when you make VCB positive here. So it's the same picture here, except that instead of VBE, we use VEB. Instead of VBC, we use VCB. All right, so that's one distinction that you see here. Wherever you see VBE, just put VEB and VCB. and you'll get the same other one. And the other one is, of course, the direction of the currents. The current direction that you can see here is different here. Current flows into the emitter. That is shown by the arrow also. Current flows into the emitter and therefore comes out of the collector here. And so that distinction is there. Otherwise, the models and everything else is similar here. So the differences are, look at the diode here. Diode is in this direction here. Base current comes out. Collector current comes out. Emitter current goes in here. Okay, so these are the distinctions to keep in mind when one is using a PNP transistor. Otherwise, early effect, current gain, everything else is the same. Okay. Any questions? Any clarifications?